Right, let's dive into this explainer and really unpack how high observability systems are fundamentally changing the way we debug our software. I mean, if you've been working in systems engineering for a while, you know the traditional drill all too well. It's 3 a.m., the pager goes off, your heart rate completely spikes, customers are getting 500 errors on the main checkout page, and the company is literally losing thousands of dollars a minute. So, in that moment of sheer, total panic, what do? Well, usually you fall back on past experience, right? You instinctively guess what's wrong based on what broke last week, you check the usual suspects, but here is the hard reality we all have to face right now. As our systems grow exponentially more complex with microservices and wildly distributed architectures, that old reliance on gut feeling, it is completely breaking down. It's just impossible to keep the whole system in your head anymore. So today, we're exploring a really critical shift. We're moving away from that frantic late-night intuition and adopting a highly structured, data-driven science. To get there, we're going to break this whole thing down into 5 really digestible parts. We'll start with a philosophical shift in debugging, jump into the mechanics of the core analysis loop, look at how we can actually automate that process, explore the role of AI agents, and finally, we'll reveal the absolute foundational requirement for making all of this work. Okay, let's jump right into section 1, the paradigm shift. And we're going to start by validating a pain point we all definitely feel. Jumping to the right answer intuitively just doesn't scale anymore. Think about a low observability world for a second. The undisputed hero of the day is always the veteran engineer. We all know this person, right? The one who's been at the company for 6 years and possesses this deep, implicit mental model of the entire architecture. They essentially use pure intuition to fix things. When something breaks, everyone crowds around their desk, just waiting for them to work their magic. But look, relying on a few system wizards is a massive bottleneck. It doesn't scale at all, it leads to total burnout for those specific individuals, and honestly, it leaves the rest of the team feeling completely helpless. Now, in a high observability environment, you don't need a hero, you need a process. You debug from first principles, driven entirely by data and hypotheses, turning debugging into a rigorous, repeatable science that literally anyone on the team can execute. Think about how we typically debug from known conditions. Let's say we just shipped a new front-end feature and performance suddenly tanks. We might immediately ask, hey, how much did our CSS and JavaScript asset sizes change? Or if we're stressed about a massive new enterprise customer onboarding, we might instinctively filter by their team ID to see if their queries are the ones clogging up the database. And while it's totally natural to jump to these questions based on what we're familiar with, this method completely fails when you hit what we call unknown unknowns. An unknown unknown is a failure mode you could never have predicted in a million years. Imagine a perfectly normal background job colliding with a minor database latency spike right as a specific subset of users on some outdated iOS version try to upload a highly specific image format. No human intuition is going to guess that bizarre, multi-causal chain of events. When you have absolutely no idea what is actually going wrong, guessing from known conditions is just wasting valuable time. So the absolutely crucial point here is that proper science requires we stop assuming. Instead, we have to systematically propose, test, and refine our hypotheses based on actual telemetry. It's kind of like a detective arriving at a really complex crime scene. The worst detective assumes the butler did it based on past cases and only looks for evidence to prove that one theory, completely ignoring everything else. A first principles detective doesn't assume anything. They follow the forensic evidence exactly where it leads. You have to start by questioning everything you think you know. You look at the raw data, you form a hypothesis about what is happening, and you test that hypothesis directly against the system's output. And if the explanation doesn't perfectly fit the observed behavior, you throw out the assumption and you iterate. Let's move right along to section 2 and see how this mindset builds into a structured, repeatable methodology, the core analysis loop. By definition, this loop is the thing that allows us to objectively sift through the noise and locate the actual signal, without relying on those pre-existing mental models we just talked about. When an incident happens, you are essentially looking for a needle in a haystack of telemetry. But the huge problem with modern distributed systems is that the haystack is constantly moving, and it's practically shouting at you. Normal system noise is incredibly chaotic. At any given second, there are always minor errors, tiny latency spikes, and network blips happening across a perfectly healthy system. It's never just a flat, peaceful green line. So the core analysis loop acts as your ultimate metal detector here. It provides a methodical approach to cutting through all that totally normal chaos to find exactly what is different about the failing requests compared to the successful ones. What's really interesting here is how this process creates a continuous, tight cycle of iteration until your explanation perfectly fits what you're observing. It's a relentless, step-by-step methodology. You always start by asking what exactly you are trying to understand. Then you visualize the data to see the shape of the problem. You search for common dimensions within that shape. You isolate the anomalies, and then, this is the important part, you ask a new, much more refined question based on what you just learned. You just keep running through this tight circle, zooming in closer and closer until the root cause becomes blatantly obvious. Let's actually apply this to a concrete real-world scenario so we can see how it works. Imagine the checkout cart on your e-commerce site is sporadically failing. We start with that prompt, a spike in pager alerts about failed checkouts. From there, we visualize the telemetry data. We might look at a heat map of latency and error rates to find exactly where those performance anomalies are hiding. Next, we group or filter for common dimensions within that specific anomalous area. Are all these failed checkouts coming from the same region, the same browser type, maybe the same application version? Finally, we isolate the likely dimensions that identify the source. Maybe we discover that 100% of the failures are isolated to a specific payment gateway in the EU West region. Now, if that still isn't the final root cause, we simply take this freshly isolated data and run it right back through the loop, digging even deeper into that specific gateway's behavior. This method is fantastic because it truly democratizes the act of debugging. It means that even newer engineers armed with a bit of curiosity and this structured loop can actually solve multi-causal nightmares. In microservice architectures, it's really rare that just one single thing breaks. Usually it's a cascading failure where like 13 different things go wrong all at once. A small network blip causes a retry storm, which exhausts a database connection pool, which crashes a critical pod, which finally triggers that user-facing alert. You no longer need the one senior engineer who wrote the original service 5 years ago to untangle this massive mess. The data literally leads the way. This levels the playing field, drastically reduces burnout for your senior staff, and accelerates resolution times across the entire team. It makes everyone a highly capable investigator. Now, while the manual loop is great and fundamentally necessary for understanding the mechanics of an investigation, cycling through every single dimension by hand just takes way too long when the system is literally on fire. Which brings us to Section 3, automating the brute force. So you might be asking yourself right about now, how do we actually scale this brute force search across hundreds of dimensions without losing our minds? Because modern systems emit an unfathomable amount of context. Every single request might be tagged with a build ID, a region, a customer tier, an instance type, a container version, and honestly hundreds of other attributes. The human brain can realistically only hold maybe 3 or 4 dimensions in its working memory at any one time. Manually clicking through and checking every single tag and attribute out of hundreds of thousands to see which one correlates with an error spike, that's simply not a human skill task. It would take hours, if not days, to find that needle. But the answer to this is remarkably elegant. We just let computers do what they do best. The system retrieves the anomaly data, which are the failing requests, and the baseline data, the healthy requests. Then it simply diffs them against each other and instantly ranks the causal factors for us. Let's break that down. Imagine you're looking at a huge crowd of 1,000 people, and you need to figure out what a tiny, tiny fraction of them have in common. It would take a human forever to scan that crowd. But a computer? It can look at that crowd and instantly highlight the only 10 people who are wearing blue hats, standing on one foot, and holding a broken product. Rather than you poking around in the dark, the observability tool looks at all the normal traffic, looks at all the failing traffic, and essentially says, hey, 99% of these errors share this exact build ID and this specific container version, whereas the successful traffic completely locks those traits. It rapidly points you to the most likely suspects in literal milliseconds. As this quote emphasizes, we definitely aren't replacing human intelligence here. We are just offloading the tedious data crunching so you can focus on making actual engineering decisions. You are still the lead detective on the case. The computer is just your highly efficient lab technician handing you the DNA results. The tool hands you the highly correlated dimensions on a silver platter. But you, the human, still have to look at that correlation, apply your unique engineering context, use your own judgment to determine actual causality, and plan the ultimate fix. This naturally leads us to Section 4 and the role of AI agents, which serve as the absolute ultimate accelerants for this automated process. AI is fundamentally changing how we interact with our telemetry. But we absolutely have to remember that AI lacks our implicit context, and it might run multiple incorrect queries while trying to freshly reconstruct the state of the system. And AI doesn't inherently know your company's lore. It doesn't know that Service A is this fragile legacy component that your team actively avoids touching. It doesn't know that Jim in accounting runs a massive, wildly unoptimized batch job every single Tuesday at 2 p.m. that temporarily throttles the database, triggering a very specific, totally benign error code. To the AI, it's all just raw data. It might make decisions or chase down rabbit holes that seem completely irrational to a human observer, precisely because it's missing that undocumented, implicit knowledge that lives exclusively in your team's collective memory. Therefore, your new role as a human operator is to provide the absolute best context and information to steer the AI agent toward the correct conclusion. You are the strategic guide here. AI isn't here to replace the engineer. It's here to elevate you from a manual data cruncher to a high-level decision maker. When the AI surfaces a potential cause, you refine its investigative path, you correct its misunderstandings based on your deep company context, and you leverage its massive processing power to iterate through that core analysis loop way faster than humanly possible. Finally, we've arrived at section 5. Let's look at the absolute prerequisite required to make any of this, manual, automated, or AI-driven, actually function. Because none of these advanced workflows just magically happen on their own. The foundational truth is this: without arbitrarily wide structured events, neither human nor machine can perform this core analysis loop. Let's define exactly what that means. If your telemetry just consists of traditional pre-aggregated metrics, which are essentially just raw numbers on a dashboard somewhere, or unstructured text logs, which are just messy strings of text, you simply cannot dynamically group, filter, and diff dimensions. You literally cannot isolate anomalies if the context wasn't captured in the first place. An arbitrarily wide structured event is kind of like a highly detailed, incredibly rich receipt of a transaction. It contains every conceivable piece of context about a single request: the user ID, the shopping cart size, the exact database query execution time, the server region, the code commit hash, all in a beautifully structured, easily queryable format. You absolutely need these rich, wide events to power this entire scientific methodology. So I'll leave you with this final, somewhat provocative thought. Looking at your own systems right now, is your telemetry actually ready for first principles debugging? Or are you still out there blindly relying on the intuition of a few exhausted veterans, just hoping for the best when things inevitably break in the middle of the night? We've journeyed from the old days of the intuitive wizard to this modern era of automated, AI-assisted scientific rigor. But as our systems continue to get weirder, more distributed, and infinitely more complex, debugging as a data-driven science isn't just a nice option anymore. It's an absolute necessity for survival. Thanks for joining me on this explainer, and I really hope this gives you a powerful new framework for truly observing your software.